So for this first one, the given series, they gave you it as the terms written out as a sum, and it shouldn't have been too hard to come up with this as the general formula for that sequence. You had 1 over 2 squared, 2 over 3 squared, 3 over 4 squared. So hopefully we could all come up with that general formula of n that represents that sum that they gave you. And so when you look at this sequence, so really, for very large n, what does this sequence eventually become for very large n? Yeah, n over n squared, which is? Now, is this larger or smaller than 1 over n? So n over n squared plus 2n plus 1. Can we use comparison? Can we use direct comparison? So first of all, the sum of 1 over n converges or diverges? It's the harmonic series. It diverges. So if we sum up that, it diverges. Now this. So if this were bigger, if all these terms that we have are bigger than the one we know diverges, by direct comparison, it would be divergent. Are all these terms bigger or smaller than these? So can we use direct comparison to claim this is divergent? We can't, because we have something, every term is smaller than the terms of a divergent series. Jury's out, okay? So in terms of using direct comparison, you can't use direct comparison. But because of this very fact, there's another test that would show this formally, but we didn't take the time to learn it. The fact that the sequence is essentially 1 over n for very large n, and that's divergent. You know, n is just going to keep getting bigger and bigger and bigger, and this is going to be minuscule. It's going to be nothing compared to the fact n over n squared. And so because 1 over n is divergent, even though it's not direct comparison, we can still say divergent, because essentially when n gets very large, we have the harmonic series, or something, getting closer and closer and closer to it. Okay? So we can't use direct comparison, but we can just reason that this sequence is essentially 1 over n for large n. 1 over n is divergent, so this is divergent. There is a test to prove that, so that's not proof. There is a test to prove that. We didn't take the time to learn that test. So for our purposes, we look at what the sequence does for very large n, and then we can say, all right, ours is going to converge or diverge just like 1 over n diverges. Okay, what about this? So this one. So here, again, think about very large k. For very large k, what will this thing do? K squared over what? K, you should see k squared over k cubed. For very large k. And that essentially is 1 over k again. So it's divergent, right? No, there's something else here, right? What else do we have? It alternates. And so since it alternates, the alternating harmonic series is convergent by the alternating series test. All that thing in red has to do is decrease to 0. It doesn't matter how fast or slow. If it alternates, and the sequence that I've circled in red, if that decreases to 0, the alternating series test says that converges. And in fact, in this case, we can also throw in direct comparison and say, hey, look, we have something less than a convergent alternating series. Our terms are less than because of the plus 1. But the plus 1 is really a moot. It's just really not very significant. just see that for large k, we essentially have k squared over k cubed, or 1 over k, and then we have alternating. So this is essentially the alternating harmonic series which converges. Okay, next one. So stop me if you have a question. Please stop me. Yes, again, conditionally convergent because it's the alternating harmonic series. Without the alternating part, we're back to the harmonic series, which diverges. So yes, this one would be conditionally convergent. Conditionally convergent. Okay, next one. Next one is a good one for the ratio test. So if I can do that fast, e to the k plus 1 over k plus 2 factorial, k plus 1 factorial, e to the k. Okay, the alternating, since it's absolute value, the alternating, the positives and negatives just go away, so I'm just not going to include it. So we have 1e on the test. So what? K plus 1 e's multiplied together and k e's multiplied together in the bottom means one more e on the top than on the bottom. And what about k plus 1 factorial over k plus 2 factorial? If you're not sure and you need to write that out, write it out. But k plus 2 factorial is essentially k plus 2 times k plus 1 factorial, right? K plus 2 times k plus 1 times k minus 1. So when you divide those, all you have is that first factor k plus 2. So we're looking at the limit of this as k gets really big. And the limit of that as k gets really big is 0. Clearly, less than 1. Conclusion, absolutely convergent. Absolutely convergent. It doesn't need the negative 1 to the k plus 1. E to the k over k plus 1 factorial is going to, that sequence is going to get to 0, and it's going to get to 0 plenty fast enough for this thing to converge. So absolutely convergent. Questions on that one? Ask if you're not sure. Ask if you're not sure. Last one, 2 over k squared minus 10. Okay? So what I notice here is 1 over k squared. How does this compare to 1 over k squared? Bigger or smaller? We're multiplying by 2 and we're subtracting 10 from the denominator. Okay, so what we have is something bigger than convergent. So by direct comparison, can we make a conclusion by direct comparison? We have something larger, terms that are larger than a series that converges. That's a convergent p-series. Is it? No. Did I get this wrong? Yeah, convergent p-series. That's a convergent p-series, and we have something larger. So can we use direct comparison to make a conclusion? No, if it's convergent and you have something larger, jury's out. Could be convergent, could be divergent. Okay, so, but back to reasoning in number 1. This is essentially like 1 or 2 over k squared for large k. When k gets really, really big, the minus 10 is it's like nothing. It doesn't have any effect really in the long run when k gets really, really large. So this is essentially compared to 2 over k squared, which is convergent. Again, we can't use direct comparison, but we can just reason and say when k is really big, we essentially have a convergent p-series, therefore convergent. Okay, last chance. Hope that helps. Okay, so you have web work for Wednesday, which is more practice of what we've done, this stuff, and a lot more ratio test, plus the new stuff we're going to do today, which is called Power Series. So get started on the web work tonight so you can make it to office hours tomorrow. It's maybe a little bit longer. Okay, this one for Wednesday may be a little bit longer. Get started tonight. Okay, I think we've mentioned this. So power series. We've mentioned this before. This is our geometric series, right? And we all know we can write out the terms really easily. A plus AR squared plus AR cubed. And I mentioned before that we could also rewrite this with the index starting at 0. So we've done most of our series with the index starting at 1 because of the transition from sequences. With sequences, we want n to start at 1 so that n means which term in the sequence we're talking about. First, second, so you don't have a 0th term in the sequence. But now as we're moving into power series and other things, we're going to see lots of series that start with n equals 0. So what would the formula, how would the formula change for n equals 0 so that we get the exact same terms added together? We want to have the exact same series, but starting with n equals 0 rather than starting with n equals 1. So what will the new formula be? Yeah, we've done that before, and that should be really easy to see that now AR to the n starting n equals 0 generates the exact same sum. Starts with A, then AR, then AR squared. And we called this idea shifting the index. This was the idea of shifting the index. And we're going to need that technique to actually solve some problems, and we're going to start representing functions with series, and this idea of this technique of shifting the index is going to be important. So we have to so notice when we reduced n, we started at n value 1 less than before. So we started at n equals 1. Now we're starting at n equals 0. What happened to the value of n in the formula? So we went from n minus 1 to n. So what just happened to that exponent? It went up 1, right? So if we start at and it should make sense. If we start at an earlier value of n, then we got to increase the value wherever n is in the formula to compensate for that. So if I'm going to start at 0, that means I've got to crank up that exponent up 1 so that I get the same terms. Should make sense. So if this goes down 1, then to compensate and get the same exact terms in the formula, we got to go up 1. Okay, so we'll be seeing that. So a power series looks a lot like a geometric series. A power series looks like a geometric series. So I want you to first of all practice writing out what that expression means. You see that and you think what? You see that and you think what? Go, practice that. So you should have wrote this. Check what you did. You should have wrote that. And so you notice that it looks a whole lot like a geometric series. So when you look at that right there, it has strong similarity to this version of the geometric series. But there are two differences. Okay, the first difference is what's the contrast between A and Cn? What's the contrast between A and Cn? What's A about and what's Cn? How are those? They're both coefficient, they're both values, but how is that different? What's that? Yeah, so A is a constant. A stays the same on every term, but these C's change, right? They can. The coefficient can change based on what term. It's a function of n, right? So it can change based on what term you're at. And what's the second difference between our geometric series and this? So what's the difference between r and x? Okay, again, r is a fixed value, and x is like an input variable. Okay, so it's like an input variable. So in a given situation, it could be fixed, but we're considering it x to be variable. Now, it's not variable from term to term. Once x has a current value, it'll be the same x in all the terms. It's just that the x can vary.
So we're talking about all possible functions, not just one.
What's that?
We're talking about all possible functions.
Series, right. So he said, we're talking about all possible series, not just one. Exactly right. And so that's the idea of that this series is like an infinite polynomial. Okay, so a power series is like a polynomial function, but what's different? The terms just keep going and going. They never stop. You never stop adding terms. So this is our first situation where we're seeing that a series can represent a function. Okay, so that begs the question. So we have this polynomial function, this like infinite polynomial, and we're writing it as a series, and so that just begs a question. What question does it beg? What do we want to know?
When does it converge?
Yeah. So for what values of x, what input values or what range of values are we going to get a convergent series? And for what values of x will the thing just blow up? So it's like over what domain of x will the power series actually converge to a finite value? Okay, so the idea of that a series, we can write a function as a series, like an infinite polynomial. Any questions on the basics here? Okay, so here's an example. X to the n over 2n minus 1. And we're going to use the ratio test for these to find out for what values, we're going to use the ratio test to find out for what values of x will the series converge. So go ahead and set up the first step of the ratio test. Go ahead, practice. So we're going to do the first step of the ratio test. The limit as n goes to infinity of what? Okay, you should have written this. We should have the ratio test memorized by now. You should have written this. And go ahead and simplify it. Simplify it inside until you're ready to take the limit. Compare with the person next to you. Simplify. It gets it simplifies way, way down to very simple result. Compare with the person next to you. Okay, you should have gotten this. And so remember that the limit is the limit as n gets very large. So we think about these power series as there's lots of possibilities for x, but once you pick a possibility and build a series, x stays the same. So we're talking about in the series is letting the n get very, very large to include all the terms. But x stays the same as you do that. As you keep adding on terms, x is the same value. It's the same input value, just like a polynomial. Okay, just like a polynomial. So what is this limit? The limit is the absolute value of x. 2n minus 1 over 2n plus 1, that limit is 1. X doesn't care what n does. It just stays x. It doesn't care what n does. That's a different variable. So when will this converge? So we're using the ratio test. Converges for when the limit is less than 1, right? So we're asking, so for what values is the absolute value of x less than 1? Okay, between -1 and 1. So we got to solve that. So we solve the absolute value is less than 1 between -1 and 1. Now what would the limit be if x was -1? What would we get for the limit if x was -1? We get 1, and what is that in the ratio test? No conclusion. What about if x equals 1? No conclusion, right? So at the boundaries of this interval is if you plug those values in, you get the limit equal to 1, which is our inconclusive case from the ratio test. So we have to check those separately. We're going to let x be -1, we're going to let x be 1, and then we're going to evaluate the resulting series to see about these, the endpoints of the interval. So we need to check them separately. So when you're going to plug -1 into and find out what series you have when x is -1. And then it's no longer a power series. It's no longer a power series because the x is gone. And so we have the series -1 to the n over 2n minus 1. And we have to evaluate that for convergence or divergence separately. Convergent or divergent? Should know this. So this is a nice, easy one. A convergent or divergent, and for what reason? By what test? Talk to the person next to you. This is the easy one. Should be able to do this. What do you think? Convergent or divergent? It is convergent. By what test? Alternating series. Alternating series test. Just 1 over 2n minus 1 decreases to 0. All we need is for the non-alternating part to decrease to 0. That's what the alternating series test says. Doesn't matter how slow it gets to 0, just as long as it gets to 0 eventually, for large n. And then with the alternating effect, it is convergent. Okay, now we got to try the other side. When x equals 1, what series do we get? And is it convergent or divergent? And for what reason? Go. So when x equals 1, what does the power series specifically become? And is that convergent or divergent? And by what test? Go. You do it. What do you lose? Okay, now you should just get 1 over 2n minus 1. 1 to the n is just 1. So 1 over 2n minus 1, convergent or divergent? Convergent or divergent? Oh, I hope we know this. Divergent by? This is direct comparison to 1 over n. How does 1 over 2n minus 1 compare to 1 over n? 1 over 2 minus 1 over 2n minus 1 is always, those terms are always greater than 1 over n. Why? Because you're multiplying by 2, first of all, and then you're subtracting 1. So here we can use direct comparison because we have a sequence, all of whose terms are greater than 1 over n, and 1 over n does what? We know that's the harmonic series that diverges, and we've got one whose terms are all greater than one that we know diverges. So by direct comparison, this is divergent. Question?
So, but since we have the 2 in the denominator, will that make it?
Oh, that makes it smaller. You're right. Yeah, you're right. Sorry.
Factor
So,
out of 1/2.
what's that?
Factor out of 1/2.
Yeah. So yeah. So we could do this. We could do. Like that. So 1/2 over 1 times n minus 2. So the 1 over n minus 2 is bigger. Yeah. And then the 1/2 is inconsequential. If it would diverge, 1/2 of a divergent series diverges. If it converges, 1/2 of a convergent series converges. So really the n minus 2 is
N minus 1/2.
what?
N minus 1/2.
No. Yeah.
The 2 times 1/2.
Thank you. Same idea. Okay, thank you. All right, so final conclusion then. So now we have all values of x for which it converges. What are all values of x for which the series converges? Well, we knew from before, definitely between -1 and 1. And then we also got another value, x equals -1, but not x equals 1. So this is called the interval of convergence. The interval of convergence, all possible values of x, that if you picked one of them, would give you a convergent series. So what's the center of this interval? What's the center of the interval? What's the center? So here's a number line version of that. What's the center of
0.
0, right? 0 is right in the center of the interval. And so because we have like a center and an interval out from the center, you can kind of think of it like a circle. Okay? You can kind of think of the circle as like representing where it converges. Inside the circle is values for which it converges. So then we have this thing called the radius of convergence. The radius of convergence. So for this one, be r equals 1 because it'd be the distance from the center out to the end of the interval. So that's often this is kind of how we frame the solution to a power series. It's like we're asking for what's the interval of convergence of the power series, or what's the radius of convergence of the power series. Now the radius doesn't tell you anything about the values for which it converges. It just tells you how big the interval is. Okay, but the interval then gives us actual values for which it converges. So you can have a radius convergence for x values like at 100, right? So like from 99 to 101. That also has a radius of 1. Okay? So that radius doesn't tell you anything about what x values are making it converge. Just gives you information about how wide the interval is. Questions on this example? Anybody have a question? Okay, let's try another one. So you're going to use the ratio test. Remember, x is independent of n. Okay? You're going to use the ratio test. You're going to let that limit as n goes to infinity. But X itself doesn't care what n does. Okay? X itself doesn't care what n does. It's its own input variable into this expression. So set it up, get started, see how you do on the ratio test. So what are we after? We're after the interval of convergence and the radius of convergence for this power series. Interval and radius. See how you do. Go. Okay, question. help, get help. Okay, what is this limit? See, you have to really remember the question we're asking. What is this limit now? As n gets very large, what happens to that expression? 0. Doesn't matter what x is. What if x were 10? What would the limit be? 0. What if x were negative 1,000? 0. Right? N is getting large. N is getting really big. And so it doesn't matter what x is, that thing is 0. So what question are we asking? For what values of x, does it converge? So for what values of x will that thing converge? It's the values of x that you'll get a limit less than 1. So for what values of x do we get a limit less than 1? Any value of x. That limit is going to go to 0 because of the nature of the expression with n's. It's going to be 0 no matter what x value you have. Do you see that? This is a really important point. Can you see that no matter what x you have, when you take the limit as n gets big, that thing will go to 0, which is always less than 1. So what's our interval and radius of convergence? Yeah, so it's any real number. All real numbers x. So our interval is any value of x. The radius is any radius. This is really important that you understand what's going on here. It doesn't matter what x is because of the nature of the expression we got. That limit is 0 no matter what x is. It's not the limit as x goes to infinity. It's the limit as n goes to infinity. Yeah, so if this is hazy, then you got to later tonight. You got to go over this example again and chew on it again. Question?
Yeah, but who's squaring infinity over basically more infinities?
Infinity is not a number. You can't think of infinity as a number. X is going to take on a particular value to get us a series. So let it be a trillion. Let x be a trillion. Now you have a trillion squared over 2n plus 3 times 2n plus 2 as n goes to infinity. Now n is going to be a lot bigger than a trillion. Like you can make n a trillion to the trillion power. So it's going to, no matter what x value you pick, that denominator is going to get much, much bigger than any x value you could ever pick as n gets infinitely large. Does it better? Does that make sense? Are we good? Does that make sense? X is, so this means that you can pick any real number. X doesn't equal infinity. Values don't, for our purposes, you don't plug infinity into something. What this conveys is that you can pick any finite value that you want for X. You can pick any finite value that you want for X. Like a trillion, or like a Google. You know what a Google is? 10 to the 100, okay? 10 to the 100 is a Google. So let X be 10 to the 100. What's that limit going to be? 0, because n is going to eventually be 10 to the 10 to the 100. Right? It's going to be much bigger because it's just going to get infinitely large. So no matter what X value you pick, no matter how large, n will get infinitely larger than that because it's the limit as n goes to infinity. Let's see if we can crank this one out fast. I'll just do it. You have lots of power series examples in your homework, plus more review from previous stuff. I did it fast, okay? X to the n plus 1 over x to the n is x. We got n over n plus 1, and we got 1/2. What does this equal? X over 2. When we take the limit. So I should have put limits in front of these. Sorry. All right, so when I take the limit, of this, I don't get 0, I get x over 2. Because this limit is 1. It's not 0, it's 1. So now, after I take the limit, I have the absolute value of x over 2. I don't have 0. So now x comes into play. So that thing has to be less than 1 for the ratio test to tell us that this series converges. So then we got -1 is less than x over 2 is less than 1, which means that x has to be between -2 and 2. What's the radius of convergence? Here the radius of convergence is 2. The center is 0, the radius is 2. I'd have to check these. We're not going to do that. But what would you do? You take -2 and you plug it in for x. Then take 2 and plug it in for x. You got 2 more series to evaluate there to find out if -2 results in convergence or if 2 results in convergence. It may be neither. It may be both. It may be one or the other. But you plug -2 in for x, and now you've got a series like we've had before. And you plug 2 in for x, and now you analyze a series like one we've had before. And then once you do those last 2 things, then you've got your final answer. So we don't have time to do that. But for sure, values between -2 and 2 make it converge. But the jury's still out on 2, and the jury's still out on -2.